There's a problem in the book on page 113. It's number 70, and it's a problem about a grocery sack. Okay? And so, you guys know me. Every problem starts with a picture, okay? And that's so you can keep track of all your forces. I didn't really like that line. Okay? And so what we have is a grocery sack sitting on the counter, and so here's my grocery sack sitting on the counter. Okay? And somebody's going to go ahead and pick it up. And it says a grocery sack can withstand a maximum of 230 newtons of force before it rips. And it says, well, a bag holding 15 kilograms of groceries, so this is 15 kg, that is lifted from the checkout counter at an acceleration of 7 meters per second, so it accelerates up at 7 meters per second. Will it hold or will it rip? Okay. Now here's how most people do this problem. They say, okay, Newton's second law is F equals ma, and so we get force equals mass 15 times the acceleration, which is 7, and 7 times, okay, this is 105 newtons, and so since the bag holds 230, they'll say yes, the bag holds. And they're entirely and completely wrong. This is bad. Okay? And the reason this is bad is because the forces never got labeled and you didn't actually think through the problem. Okay? Right now this bag is sitting on the counter, okay? Which means there's two forces that are acting on it. There's the force due to gravity, which is Fg, right? And the counter's pushing back on it with another force called the normal force. Okay, that's Fn. Okay? Now, here's what I want you to think about. As this bag gets raised higher and higher and higher, a force starts to get applied to this handle as another force. So there's actually a third force here. Here's my third force. This is the applied force, or the force that's lifting it up, and we call it FL. As this lifting force gets bigger, the normal force gets smaller and smaller and smaller because the counter has to support less and less and less of the weight. So eventually the normal force goes away, and the only thing acting on this bag is the lift force and gravity. And that's what I want to consider. I want to consider as this bag is accelerating up, and the only two forces acting on it are the lift force and gravity. Because Newton's second law does not say force equals mass times acceleration. Newton's second law says net force equals mass times acceleration. Which means you got to add all your forces together first. Which means I have to take FL, the force that's picking it up, the lifting force, plus Fg, and set that equal to ma. Now here's what I know. I know positive is the upward direction. Okay, I know the mass of the bag is equal to 15 kilograms. I know the bag's acceleration is 7 meters per second. I also know the acceleration due to gravity is negative 9.8. It's negative 9.8 because I chose positive as up. Okay, so now I'm going to sub in every value I know for this. FL, I don't know what FL is. Okay, plus Fg. Fg is mass times the acceleration due to gravity, so this is mg, equals ma. One more step to sub in what I know. Okay, so FL I don't know anything about. Plus m, well I do know m, that's the mass of the bag, that's 15, times g, which is 9.8, but it's negative 9.8 because it's down, equals m, 15, times a, which is 7. Okay, that means FL plus a negative 15 times 9.8 is 150 minus 3, 147 equals 105. Okay. I add over that 147 and I get the lift force equals 252 newtons. The bag rips. Okay. The bag can only hold 230 newtons of force. And so the problem most people have is they forget this one right here. This is weight. This is the force due to gravity. Okay. Just to hold this bag, just to hold it, takes 147 newtons of force. To actually cause it to accelerate up is going to take another little bit of force. So this side, this tells me what it gets to accelerate up. This tells me what I have to do just to hold it up. against gravity, just to hold it. Okay? So the total force to hold it and accelerate it is 252 newtons. Okay? I want to kind of look at a similar problem. It's the problem on the quiz with the cart. Okay? And the problem said, hey, here's a cart on a surface being pulled along by a string, okay? And this string goes over a pulley, it's connected to a mass, and the mass is going to pull the whole thing down. Okay? And I think I said, I can't remember now, I think I said the mass of the cart is 2.5 kilograms? I better check. 2.4. Okay. So the mass of the cart, so I'm going to say MC equals 2.4 kilograms. Okay. I also said the cart accelerates, so AC, at 1.6 meters per second. Okay. Now, I ask for two things in this problem. One is the force on the cart. Okay. The other is the mass of this thing. So I'm going to call it mass M. Okay, those are the two things I want out of this problem. As always, start with a picture with all your forces. Since I have two objects, I'm going to have kind of two pictures. There's this force pushing up, that's the normal force. There's this force pushing down, that's gravity. Okay, those two forces, since this thing's not moving up or down or accelerating up or down, those two forces cancel. So I don't have to worry about those. Fn plus Fg equals 0. Okay, so those cancel out, I'm not worried about them. There's one more force here I do have to worry about. It's this force. This is the tension force, so I'm going to call it Ft. Okay, and that's what I'm actually supposed to find. How big is that tension force? Okay, well, I need a positive direction, so I'm going to assume to the right is positive. And now I can say, all right, net force is tension force because there's no other forces acting on it, and that equals mass times acceleration. And so now I can just say this is equal to 2.4 times 1.6, which is 3.84 newtons. Okay, so it takes 3.84 newtons of force to accelerate this thing in this direction. Okay? The second part of this problem is where it gets a little bit tricky. Okay? And so we're going to go ahead and look at this mass down here. Okay? There's two forces acting on the mass. Gravity's pulling it down, but tension in the rope is actually pulling it up. Okay? And so this is in the y direction, so I'm going to assume the up direction is positive. Now, this is an interesting problem for a couple reasons. One, this rope is connected here, and we're going to learn later, and you can assume now, that the tension on one side of the rope is equal to the tension on the other side of the rope. Okay? Otherwise, the rope would have to stretch or break or something. The other thing that's going on here is this thing is actually accelerating down. Okay, it's falling down. So my positive acceleration over here of 1.6 is actually a negative acceleration over here. So when I'm talking about the mass, it is a completely different object. So I'm going to say the mass is unknown. That's what I'm trying to find. I know its acceleration is negative 1.6. It's accelerating down. Now, what would it be doing if it was just free fall, if this chord wasn't here? How fast would it accelerate? Well, it would just be g, and that would be 9.8. Okay, since it's not accelerating down at 9.8, we know that there has to be some force here that's acting on it. Okay? We know it's smaller than Fg because Fg is actually big enough to accelerate it down, but it's there. Okay? So acceleration is negative 1.6 meters per second per second. Ft, the force up, we just calculated it actually as 3.84 newtons. Okay? What's on one side of the rope is the same as on the other side of the rope. Fg, all I know about Fg is it's equal to mg. Okay? And I do know g is equal to negative 9.8. Okay? Which means if I do Newton's second law for this block right here, I'm going to say net force is equal to Ft plus Fg, and that equals ma. Okay, Okay, now this mass is different than the cart, but we're just dealing with the block, so that's okay. Ft I know is 3.84. Okay, Fg I know is m, I don't know m, but it's m, times negative 9.8 equals m times, the acceleration of this whole thing was negative 1.6, and so now I'm going to add over this 9.8, and I'm going to 3.84 equals m times 8.2. And now I can divide by 8.2, divide by 8.2, and I get a mass of 0.47 kilograms. Okay? So the trick to any of these problems is first set up all your forces and label them, and then try to solve them. The other trick is Newton's second law does not say force equals mass times acceleration. It says net force equals mass times acceleration. Good luck with the rest of the quiz, and remember, forces don't cause forces don't cause velocity. Forces cause acceleration. It's possible to have moving at a constant speed and have no net force.